Welcome back, everybody. Now what we're going to do is we're going to talk about a little bit of the historical context around software engineering, kind of why software engineering is its own field of study in a lot of ways, and further differentiate it from very kind of one-off development efforts that you might have been doing as a student in a computer science class. We talked a little bit about this kind of tangentially last time. What is software engineering? If you wanted to go all the way down and try to find some sort of very formal definition, it would probably not provide a ton of additional information that we haven't already covered. Basically, what software engineering is trying to take a problem and then design and implement a solution to that problem using computer components that are not hardware. And so this distinction is really based on how tangible that particular piece of computer equipment is. Obviously there are networking solutions, there are actual like processor hardware implementation solutions to specific problems. We're not so much concerned about those here, but what we're actually concerned about is generating code or software to solve real life problems. As most things in life, these sort of components exist on a continuum. We always have things like firmware that's somewhere between hardware implementations and software. And in a lot of ways, firmware acts and walks and talks a lot like software. There is quite a bit of firmware development that takes place exactly along the same lines of the processes that we're going to talk about in this course. The most important thing, regardless of how you define software engineering or any of that, is that you want software engineering to be these three things. You want it to be structured, you want it to be metered, and you want it to be towards some sort of central component or some central purpose. Structured, meaning that it's repeatable. You can actually pour whatever requirements into the big machine you want and get meaningful software out. Metered, meaning that you have a finite timeline that you can develop against, and that you're not wasting resources or using too few resources on the task at hand. You also want a purpose, because without the problem that you're trying to solve, it's really not engineering. What you're doing is you're developing a solution for maybe a problem that hasn't been thought of yet. That's more of a research activity. One of the essential things we talked about last time is the fact that life on Earth is complicated. It doesn't even really matter if you don't think that your job is complicated. Your job without software would be substantially more complicated than it is with them. Right now, even as a student, you are probably thinking about 2 bajillion things that may or may not directly impact the next 24 hours of your life. So tomorrow, at this exact same time, you might be thinking about a million completely different topics or ideas, and just that thought experiment, beyond anything that's happening in your actual occupation, provides the context for what software is trying to do. It's trying to take all of these things out of your brain and kind of give you a way of organizing all of those things that kind of implement the life that you live. Software has become the major tool with which we rein in all of this complexity. So if you think about how you make your coffee, how you set your alarm to wake you up, from whatever thing you're trying to do, most of those items, most of the consumer electronics that you use have some software in them that attempt to make you require less information to do a trivial task. The catchphrase might be that America runs on Duncan, but it actually really runs on software. Without software, we wouldn't necessarily have a lot of the consumer electronics or a lot of the consumer patterns that we have as a society at large. So there are obviously a lot of upsides to software in general. So you get to live your life with a lot less complexity. You no longer have to deal with paper ledgers at the bank. You no longer have to deal with paper checks. You no longer have to actually show up to a place to pay them necessarily. All of these things have become easier and easier and easier as software has allowed us to kind of offload some of that work from people to machines. And one of the things that kind of goes unrecognized a little bit is that we're able to do hypercritical things very repeatably. So things like fail safes in power plants, things like fail safes on missile defense systems. These things, if they required a 72-step process for a person to do, and that person missed step 69, that could be a very bad situation. And so by using software to make all these things repeatable, we eliminate a lot of risk of just slight oversights that a human might make, causing massive problems. And so the extension of that is that automation helps us limit this sort of mindless work that humans are historically very bad at. So if you had a task to click a button every 10 seconds for 8 hours, and you gave that task to a machine and you gave that task to a human, it is almost certain that the human would fail long before the machine failed to perform that particular task. And so what we're trying to do is we're trying to identify as a culture, as a society, all of these repeatable tasks that could be given to machines, so that we're not dependent on humans trying to do things that humans are honestly kind of bad at. Unfortunately, that means that there are also some downsides to software. And so the very top one is that we've talked about how big and complicated it is. And because of those things, it's really, really hard to get any single piece of software entirely correct. There are very few pieces of software in existence in production environments right now that do not have some even minor bugs in them. And so if you think about something like Microsoft Windows, that has been around for decades, they're still releasing updates, they're still fixing issues, they're still expanding the software because it needs to do increasingly more complicated things as we go along, and people continuously kind of uncover issues with it. So the other problem is that we've talked about sort of the sociological issues around software development, but all of those social issues of working in a team make not only the process of building software difficult, but it also makes the process of utilizing software difficult. So if there's a lot of cognitive dissonance around the use of a system, it's very likely that two people who have implemented features implement them in ways that don't make sense to the user if you put them side by side. And so because software is not created by one person, the cognitive dissonance inside of the team is sometimes exposed to users, and that makes the application very hard to kind of use from a usability standpoint. And unfortunately, even though machines are really good at doing repeatable tasks, the complexity of those tasks kind of dictate how often the machine will get them wrong. So if you're talking about simply clicking a button every 10 seconds, that's one thing. If you're talking about going through and checking 2 million rules in order to ensure a safe flight between point A and point B, that latter task is obviously more prone to failure. And so as we shift all of this complexity to machines and to software, we're seeing that software failures have just sort of gradually become a part of our daily life. So even if it's totally normal to have a blue screen of death every once in a while, some of these failures are really, really bad, and their prevalence in everyday society indicates that the really, really bad bugs, the really bad software failures, are also more likely to increase in prevalence as we go down this path of making sure that everything is shifted from a human that's fallible to a piece of software that's less fallible but still fallible. So drilling down into that a little bit more, if you think about what would happen if in the middle of a morning the Brooklyn Bridge just suddenly ceased to be and fell into the river. What would happen is there would be a massive media fanfare, there would be helicopters, there would be all of this personnel everywhere. It would be a very widely publicized event, and it would clearly be a not okay situation. If you compare that to something that happens extremely frequently on your machine, like maybe a blue screen of death, you see the juxtaposition. If you have a blue screen of death that happens on a hypercritical system, that top bullet could actually happen and lead to very, very catastrophic events solely because a controller somewhere encountered some operating system glitch. So there's this prevalent thought that it's okay for software to fail because failures in software engineering are just inconveniences. They're just something that causes a blue screen of death or causes an application to crash. And the ultimate outcome of that application crashing is not all that big of a deal. So there's this idea that software engineering can't be as fatal as an engineering malfunction in, say, civil engineering or mechanical engineering. And unfortunately, that's very untrue. Software disasters themselves can absolutely lead to loss of human life. This has been happening for decades and decades and decades. One very well-documented case is the Therac 25, which was basically a controller for a radioactive treatment kind of situation. And it allowed the people being treated or the scan to actually provide too much radiation, and that's clearly a bad situation. You also have things like the Worldwide Military Command and Control System. That was a very kind of hobbled together piece of software that was tasked with missile defense, it has failed in a number of different ways. There's actually this huge PDF report about how dodgy that whole system was that's available through the federal government. So you can actually go all the way back to I think the late 70s and read about all of the different ways this thing has failed, and some of them are pretty scary. There's also more recent events, right? So Boeing 737 MAX, all of these things have a lot of impact on people, fatalities notwithstanding. So you can think about how this is only going to get worse as we push more and more and more industries and more and more and more tasks toward software and away from actual people trying to perform those tasks. And so if we zoom out a little bit and we think about all of the kind of disasters in software that don't involve loss of human life, they're also pretty bad, right? You can think about things like the Great Blackout of 2003, which was actually caused by the exact same errant code pattern that caused the Therac 25 issue. And you can see that we basically didn't learn anything from Therac 25. And so even though people actually died, we as a society, or we as a community of software engineers, allowed the exact same issue to crop up 20 years later and cause one of the largest blackouts that has ever happened in the country. We also have things that make headline news, sort of like travel delays and things like that. All of these are fundamental failures of software trying to do fairly simple things, like keep track of dates and times that airlines should be flying planes. You also see things like Silicon Valley unicorns. And so you see these companies like Knight Capital A lot of them do not have actual assets. So if you think about the fact that Snapchat and all of these other companies are publicly traded, they don't have assets that they would liquidate if they were to become insolvent. They basically just have code and they have a concept. And what this allows them to do is boom, and they can trade for very high stock prices. They can pull in tons and tons and tons of capital. But then if their software fundamentally fails and does something untoward, like Knight Capital, selling stock when it shouldn't be selling stock, they can bust in a fraction of the time that it took them to boom. So Knight Capital had been around for quite a long time, and they actually completely busted in, I think, like 12 to 16 hours, something like that, because of a single software failure. So even though not all software failures are disasters that kill people, they can kill companies, they can cause massive issues at a societal kind of level. So what can we do about all of this? We've talked about how software engineering tasks are fundamentally different from programming assignments. And the first thing that we need to do is kind of develop an idea around how do we build production level software that is repeatable. We can use the same process for building an air traffic controller as we do for building a blender controller, that we do for building a system for keeping your house reasonable temperature in the summer. If we can build these kind of processes, then we know that even the least safety critical thing that we're building has some level of safety baked into it. And so this is basically diametrically opposed to the ad hoc development process that you use for one-off programming assignments, or you use to just kind of do hobby coding. So the fundamental take-home message is that software engineering is as much about processes and patterns that you can put in place to make code safe as it is about the actual technology and the actual act of coding that you're doing to put the systems together. And so fundamentally, the goal that you have as a software engineer is to provide a software solution to a problem that is stable. It is going to work today, tomorrow, and the day after that. It's scalable. It's not going to suddenly fail when the 101st person signs on to the application. And it's defect-free. It does exactly what the client expects it to do in every use case the client cares about. But as we're going to see, all three of those things are not necessarily completely achievable all the time. So if we drill down into how things used to be, so the kind of classical software development model, before we were talking about artificial intelligence, we were really kind of talking about the dot-com boom, the idea of putting all of the information that we had on the internet, building websites that would let you do things like schedule appointments or display the menu for your restaurant and that kind of thing. And even before that, we had this massive avalanche of demand for software programs that could do things like launch rockets, so that people didn't have to do all of these calculations by hand. And so the demand for software vastly outpaced the kind of metered approach of building processes around how you generate code that is stable and scalable and defect-free. So from the very beginning, we kind of have this debt looming over the whole study of software engineering. You have a whole bunch of work to do, you have no time to do it in, and so we kind of start off in a car with square wheels. And so because of the lack of time to kind of think through this at a sort of meta level, we began using a process commonly referred to as the waterfall methodology, which is rooted in ideas from sort of construction, mechanical engineering, manufacturing, that kind of thing. And so the idea behind this development model is that all of the phases of development they are grouped sequentially, and they have strong dependencies from between one another. And so in order to go to phase 2, you have to have phase 1 entirely done and sort of tested and signed off. In order to go to phase 3, you have to have phase 2 entirely tested and signed off. And going backward from phase 3 to phase 2 is strictly not allowed. You have to kind of redo the whole thing and take inventory of how the changes are going to fundamentally impact the system. So if we think about what this means from a kind of infographic level, kind of zoomed out, what we have when we're trying to build a building, for example, is we want to go out, we want to draw the blueprints for what the building looks like, we want to go to the city and ask them for permission, basically. This is how many bathrooms are going to be on level 1, this is going to be how many fire escapes are in the building, etc., etc. Once you get that approval, then you want to move on to actually the nitty-gritty sort of brass tacks. You want to go to the site and prepare it, you want to dig and level the ground, you want to pour the foundation, and then you actually start framing the building up, putting all of the walls together, and then you do the plumbing and the electrical and the drywall and finishing touches and all of that kind of stuff. And so from a perspective of building a building, this waterfall approach totally makes sense. It does not make sense to suddenly, during the framing stage, have to go back and ask for permits for the wall that you're building currently. That doesn't kind of make sense. The problem is that fundamentally software is not a building. When you're trying to plan a new office building, you have to go through this very kind of arduous process of trying to understand how many rooms need to be in the building, what are the requirements of the city or the county or the state for what the arrangement of those rooms are, etc. And once you go into that second phase where you're actually pouring concrete into the ground, if a client comes and sees that the plumbing is not necessarily where they want the plumbing to be, it's very obvious for them if they want to dig up a bunch of concrete and move a pipe 10 feet across the room, that's going to cost them a lot of money. That is not true in software. In software, you can show a client a website, and the client can want the website to look slightly different, and depending on what that change is, it could fundamentally change the code that you have written underneath the website. And while it looks like all you want to do is remove a painting and then hang another painting under the covers, so to speak, it's a fundamental shift closer to moving a pipe out of concrete to a different room. And so that kind of thing is not obvious to the stakeholders, the people who are actually paying for the project, but in a lot of cases it's not even really clear to the development team, because not all of the development team is going to be versed in all of the different pieces of the system. And so they may think that a change is very, very small, but they could be very, very wrong about the impact of that change. So if we want to map the waterfall model to software, it would look something like this. You would want to go to the client, you would want to gather all of the requirements of the system that they want you to build, and then you would want to sign off on what those requirements are. Then you would develop a specification based on those requirements. You would go back to the client and say, hey, are these specifications okay? This is the design that we want to build the application from. You would get approval on that. And then you would actually go out and you would build the system. Then after you built the system, you would go, you would do some testing on your own, you would hand the system off to the client would do some testing, they would sign off on it, everybody would get paid, they would get their system, everybody's happy, the world moves on. The problem is that in software engineering, or in software in general, change is the only thing that you can 100% guarantee will happen during the project. So what's very likely to happen is you're likely to get to the build the system phase. You have gathered all the requirements, you have developed the design, the specifications, maybe those things have already been signed off on, the client's happy, you're happy, and then suddenly somebody at the client starts screaming, running around, and says, oh, by the way, we don't have modern computers. The system that you're building to run our bank has to run on this ENIAC that we have in the sub-basement, and you only have 64 KB of memory in order to run the entire thing top to bottom. We don't have a file system. Everything has to be stored in, some alien electronic form. And so at this point, you are kind of stuck in the mud. You have started creating an application that is not going to work for the client, not because of a lack of requirement gathering. You've gathered a bunch of requirements. You just missed the one that actually mattered. And maybe this is such an esoteric kind of thing that only one person at the client actually knew that it was true, and that person was not a person that you talked to. You're not going to necessarily know who all of the true stakeholders are when you first start a project. And so now what's going to end up happening is you're going to have to throw the entire thing out of a window and start over again. The problem with that is you have paid a lot of developers to do something that nobody's going to potentially pay for. It's really up to how the agreement was drafted. So you get the pleasure of drafting an email that goes something like this. Dear client, we're all the way back at square one, even though we spent 6 months trying to develop a system because John told us that now we have to run everything on a machine from the late 60s. So you're going to get this massive bill, and you need to pay the bill because we need to pay the people to actually generate the thing that you need. Sorry, you didn't give us all the requirements. Have a nice day. These emails don't typically go well because the client is going to feel like you should have asked all of the pertinent questions, and you, as a person who's versed in technology, versed in software engineering, probably are not going to be able to foresee all of the pitfalls. You're not going to be able to ask the person if they have a 65-year-old machine that they're trying to run this piece of software on. So while this example is extremely absurd, this is an allegory for a thing that you will see constantly, over and over and over. Clients are notorious for changing their mind, and it can happen multiple times a day, multiple times a week, certainly multiple times throughout the life cycle of a project you're trying to build for a client. So where this comes from is that the client is almost exclusively enveloped in the business problem. They don't actually care 95% of the time what the technological problems are. They don't care what platform you're using. They don't care what the tech stack looks like. They don't care what language is written in a lot of cases. What they actually want is they want the system to work and for their bank to be able to do business. They want their law firm to be able to function. And so while they are wrapped up in the business context, it's your job to pull them into the technology sphere just enough to understand what they're doing, so that you can ask them all the pertinent questions up front and get as good answer as possible. The other thing is that a lot of clients don't actually know what they want, and a lot of the times what they'll do is they will agree to something, and then they will see a version of it, and then they'll change their mind on the spot, and they'll say, oh man, this prototype is absolutely terrible, we actually want something completely different. And they will treat your software development team much like a car lot. They want to have a car built for them and then do a test drive and then tell you to fundamentally change something about the car. The problem is that that's going to cost you money to do. And so as a software organization, you kind of have to protect yourself from those changes by finding a better way of sort of allowing them to be communicated to you, but also incorporating them into the project as the project is actually going on. So at the root of it, a lot of these problems are that software engineering itself is a business. It's a business as much as it is a technological career. You will very rarely run into software engineering teams that will work for free outside of open source software. And if you and your 5 friends have this great idea to create the great new tech startup, ultimately you're going to have to pay your friends and you have to pay you in order to buy groceries while you're trying to build this piece of code. So if you have a client that refuses to pay you, you're not going to be able to pay your friends, you're not going to be able to pay yourself. And so keeping a handle on all of these organizational issues around client change requests, around what the client actually wants, and making sure that you're constantly working in that direction is paramount, because without that, you can't really have a software engineering team. So we're going to talk about this kind of idea specifically, if not in the next video, in the one after that. We need to have projects that are sustainable and they're mutually beneficial for everyone. So if the client is happy with the system that you're creating, they're going to be happy paying for it. And if they're happy paying for it, you're going to be able to very comfortably continue to do the work that you like to do. It is paramount that you're able to provide a top-notch product, which means that you're able to provide a defect-free as possible solution to the client to fulfill whatever business need they have, that they will then happily pay for because their expectations are met by your piece of software. If you are wasting time, even if it's not your fault, somebody has to pay for it, and that's a really bad situation to find yourself in unknowingly. And so the major issue with waterfall approaches is that you can find out that you have a fundamental misunderstanding of what the client needs very late in the process, and by spending all of the time between when the client recognizes they have an issue and you recognize the issue, coding software that's never going to be used, you are just wasting a lot of resources that you otherwise wouldn't waste. So to wrap it all up, software engineering itself has a ton of technical challenges. You're going to find yourself solving a lot of the same problems that you solved in data structures. You're going to have a lot of the same technological issues from operating systems. You're going to be building large-scale systems that deeply have technology ingrained in them, and you have to know all of the sort of technological stuff in all the other classes, but it also encapsulates a ton of organizational issues that would really be brought up in something like a communications department or a business department curriculum. So what this class is intended to do is A, kind of push you toward putting all those technological skills together in an architectural way, and B, trying to identify all of these kind of extracurricular sort of things that are involved in software engineering, the practice of software engineering, so that when they happen, you have a game plan for kind of mitigating the risk associated with them. So our goal for the rest of the class is to take a look at software development top to bottom, and we're going to look at the whole process from various points of view. And the hope is that after this whole process is done, after the semester, you will have an idea of what the software engineering industry at large entails. And so you'll be able to kind of walk out of graduation, go and get a job, and not be super surprised by anything that kind of pops up. So in the next video, what we're going to tackle is a lot of the development methodologies that help us address this fundamental issue with waterfall, and try to build software in a more reasonable way where we allow clients to change their mind, and that makes for a better sort of situation for the developers and for the client, and everybody can kind of meet in the middle in a much happier space. So thank you for tuning in, and I will see you in the next video.